So let us continue. Now we talk about a special kind of extension called cyclotomic extension. These are algebraic extensions, but of a certain kind. Okay, these are algebraic extensions involving only roots of unity. Okay, only roots of unity, nothing else. Okay, so for any positive integer n, let zeta n be the nth primitive root of unity, which is e raised to 2 pi I by n. Okay, by Euler's formula, this is actually cos 2 pi by n plus I times sine 2 pi by n. Okay, cos 2 pi by n plus I times sine 2 pi by n. That is what this complex number is. The primitive nth root of unity. Then all the nth roots of unity are just powers of zeta n from 1 to n, right? So zeta n raised to k, where k going from 1 to n. And zeta n raised to n is in fact equal to 1. Okay. So these are all the nth roots of unity. There are n of them. But what is the equation satisfied by an nth root of unity? The equation is x raised to n minus 1 is equal to 0 over the complex numbers, right? Every nth root of unity satisfies the equation x raised to n minus 1 equal to 0. And any complex number that satisfies the equation x raised to n minus 1 equal to 0 must be an nth root of unity, must be one of these. Correct? That's the definition. Okay. Therefore, when we write down the factorization over the complex numbers, a polynomial as the product of a product of linear factors corresponding to the roots, what do we get? X raised to n minus 1 is equal to product over k going from 1 to n, x minus zeta n raised to k. Okay. So these two polynomials are the same. Okay. Now what we do here is we'll just group the terms that appear here. Okay. How do we group the terms? So we are ranging over values of k going from 1 to n. Okay. Now for each k, the GCD of k with n will be something. K will have some GCD d, okay, with n. Correct? Now depending on the GCD, I will group the terms. Now we know that GCD of k and n will always divide n. Correct? So the GCD of k with n is a factor of n always. So first, the grouping is in terms of factors of n. I vary over all factors b with n, all factors b of n, and for each factor d, I look at only those k between 1 and n whose GCD with n is equal to d. And then I'll consider those products x minus zeta n raised to k. Now, do you see this double product is equal to this single product? Because for every k, there is some d dividing n such that GCD of k with n is d. And when you separate this, expand this out, you get the whole product. So the single product in the first line is equal to the double product in the second line. But now I have grouped the terms in terms of the divisors of n. So now inside we have this product of some linear factors corresponding to a fixed divisor d. Correct? Now only this product for a fixed d, right? For every d, there is this product. For every d, there is this product. So for every d, the product that we get inside this product, this we will define to be phi of n by d times n by d of x. Okay. For every d, this inner product, we will call it a polynomial phi n by d. Okay. We are not calling it phi d. That's a small notational difference that you should keep in mind. We are not calling it n. We are not calling it phi d. We are calling it phi n by d. Okay. So this is corresponding to every divisor d. The inside product that you get here, this is defined to be the polynomial phi n by d of x. Is that clear? Therefore, when you rewrite this, now when you look at what phi n by d really means, and you write down the definition of phi for a general integer m, we get the following definition. So this you should check on your own. I have written it directly. Check that when I define phi this way, for some integer m, phi m will actually turn out to be exactly this. Okay, so what is it? Phi m of x is equal to product over all k varying between 1 and m such that the GCD of k with m is just 1. Not all k varying over 1 and m, only the k such that the GCD of k with m is equal to 1. Okay, all those k which is co-prime to m, those roots of unity x minus zeta m raised to k. And this is my definition for any positive integer m. Okay, so this is the polynomial phi m of x is defined to be product over all k co-prime to m x minus zeta m raised to k, zeta m raised to k. This is defined to be the mth cyclotomic polynomial. Okay, mth cyclotomic polynomial. And what is the degree of this polynomial? Well, the degree is equal to the number of factors. Number of factors is equal to the number of k such that the GCD of k with n is 1. And do you know, this is actually equal to Euler's totient function. Number of elements which are co-prime to m and less than or equal to m. This is called Euler's totient function. You must have seen this in BSc. We have also seen how to calculate Euler's totient function when you are given a prime factorization of the number. Okay, that's not so important. So just remember that this is Euler's totient function. Okay, number of elements less than or equal to m and co-prime with m. That's the degree of this polynomial. Further, check this yourself. We also have this formula. Okay, by looking at this factorization, x raised to n minus 1 equal to product d dividing n phi n by d of x. By rearranging terms, you will get this formula. Okay, check this yourself. Phi n of x is equal to x raised to n minus 1 divided by product over all d dividing n d less than n phi d of x. Okay, check this yourself, but this is a nice enough formula and it's a useful formula. Okay. So now let's go to some properties of this phi n. So the property, two important properties is that for any positive integer n, phi n x is an integer polynomial. All the coefficients will be integers. Okay. So let's go back to the definition. Do you see the definition of phi n is this? Product over all k which are co-prime to n x minus zeta n raised to k when you look at phi n. Okay, here it's phi n, but when you look at phi n. So the product of linear factors corresponding to these complex numbers will only have integer coefficients. That is one property. Okay. Phi n of x is always an integer polynomial and it is irreducible in Qx. Always irreducible in Qx for any n. Okay, these are two properties. This is true for any n, but it is easier to prove when n is a prime. So for this course, we will only prove it for the case n equal to p, where p is a prime. General case we are not proving, but we will assume it as a result. Okay, but we will prove it for n equal to p, where p is a prime. In this case, the proof is very easy. Okay, so let's go back to the definition. The first equality that we were seeing. When you consider x raised to p minus 1, we know this easy factorization, right? This is equal to x minus 1 times 1 plus x square up to x raised to p minus 1. Simple factorization that we all know. But now let's compare this with this definition. Phi p of x then is equal to sum over all k co-prime to p x minus zeta p raised to k. Okay. Now which k are going to be co-prime to p? Now that k is varying from 1 to p. Since p is a prime, k is co-prime to p for all k between 1 and p minus 1. That's the important part. K is co-prime to p for all k between 1 and p minus 1 because p is a prime. So the only factor that we are not including here is x minus zeta p raised to p, which is x minus 1. Every other factor is included in this product because some product over k between 1 and p, GCD k with p equal to 1 is exactly product over k equal to 1 to p minus 1 because p is a prime. So the only factor that we are removing here is x minus 1. Therefore, this 5p in this case is equal to x raised to p minus 1 divided by x minus 1. Because when you cross multiply x minus 1 here, you will get x raised to p minus 1 because x minus 1 was the only factor that was missing. Okay, so this is x raised to p minus 1 by x minus 1, but then from here we know that x raised to p minus 1 divided by x minus 1 is exactly 1 plus x squared up to x raised to p minus 1. Therefore, each of these coefficients is 1 in fact. So this is a polynomial over the integers. Simple proof just by looking at the factorization. Okay. Now, how do we prove that this is irreducible? So now we will use Eisenstein and Gauss's lemma in this case in a very nice way. Okay. So we have already seen here that phi p of x is x raised to p minus 1 by x minus 1. This is also an important formula. Okay, when p is a prime. So do you see, if I try to evaluate phi p of x plus 1, you remember I mentioned this as a remark earlier. For Eisenstein, you don't need to prove that a polynomial f of x is irreducible. You can prove that f of x plus a is irreducible for any convenient suitable a, and we will still be done. So you don't really need to show that phi p of x is irreducible. You can show that phi p of x plus 1 is irreducible, and that will also imply that phi p of x is irreducible. Okay, so we'll show that phi p x plus 1 is irreducible because that is nicer, easier to prove. So phi p of x plus 1 by this formula is equal to x plus 1 raised to p minus 1 by x plus 1 minus 1, which is x. Right, x plus 1 raised to p minus 1 by x. Let us expand this by using binomial theorem. So 1 by x comes outside. This is summation j going from 0 to p, p choose j, x raised to j. Okay, just apply binomial theorem, minus 1. All right. But what is 1? What I have done here is p choose 0, the factor p choose 0 x raised to 0, that is equal to 1, right? So that cancels with this one. We have removed that. Then p choose p x raised to p, that is also equal to x raised to p because p choose p is 1. Okay, so we have separated that factor out. So p choose 0 x raised to 0 cancels with minus 1, and p choose p x raised to p is x raised to p. I have written it separately here. The remaining factors are summation j going from 1 to p minus 1, p to j, x raised to j. Okay, so separating this out, now I'll take the x inside because now every monomial here has power of x at least 1. Okay, so I can divide by x throughout. So p choose 1 x raised to 1 divided by x is just p choose 1. P choose 2 x squared divided by x is p choose 2 x, and so on up to p choose p minus 1 x raised to p minus 1 divided by x is p choose p minus 1 x raised to p minus 2, and x raised to p divided by x is x raised to p minus 1. So this is phi p of x plus 1. Okay, now we can apply Eisenstein criterion here with the prime p. Okay, why is that? Note that p choose 1 is p itself. Okay, p choose 1 is just p. So Eisenstein's criterion we will apply, and we will show what do we need. So this is a monic polynomial, of course, leading term is coefficient 1. All the lower order terms are divisible, all the lower order coefficients are divisible by p. Okay, so we need to show that p divides p choose 1, p divides p choose 2, p divides p choose 3 up to p divides p choose p minus 1, of which we already know that p divides p choose 1 because p choose 1 is p, and this is the constant term. So p square does not divide p choose 1. P square cannot divide p, right? So those two conditions are satisfied. All we need to check is whether P divides P choose 2, P divides P choose 3, up to P divides P choose P minus 1, which we will check in a little while. Okay. Let us just assume for a moment that it is true. And then by Eisenstein's criterion, with prime P, phi Px plus 1 is irreducible in Zx. But this is this is a monic polynomial. Therefore, by Gauss's lemma, phi Px plus 1 is irreducible in Qx. Therefore, phi Px is irreducible in Qx. Right? So what have we assumed here? We are assuming that P divides the binomial coefficients P choose 1 to P choose P minus 1, which we will prove a little later. Okay. So phi Px is irreducible. Is that clear? So we have proved this statement for n equal to P a prime. Okay, so this theorem is done when n is a prime. So now let us prove that P divides these binomial coefficients, because that is what we need to use Eisenstein. So why does this divide any binomial coefficient between P choose P minus 1, P choose 1 and P choose P minus 1. So let's consider any k between 1 and P minus 1, and let n sub k be the number P choose k. Let nk be P choose k. So by definition of binomial coefficient, nk is equal to P factorial divided by k factorial into P minus k factorial. Taking the terms to the other side, it means nk times k factorial times P minus k factorial is equal to P factorial. Okay. Now clearly P divides P factorial because P is a factor. So P divides nk times k factorial times P minus k factorial because this is equal to P factorial. But now, since k is between 1 and P minus 1, all the factors in k factorial are less than P. All the factors in P minus k factorial are also less than P. So since k is between 1 and P minus 1, P cannot divide k factorial and P cannot divide P minus k factorial because each of these factors, each factor in both these factorials is less than P. But P divides product nk times k factorial times P minus k factorial. It does not divide these two factors, k factorial, P minus k factorial. So P must divide nk because P is a prime. Okay. Therefore, P must divide nk. But what is nk? Nk is P choose k. Okay. So P divides P choose k. Note that this is exactly where we use very importantly the fact that k is between 1 and P minus 1. Because then P does not divide k factorial and P minus k factorial. Okay, so P divides P choose k, and this completes the proof. Then we can apply Eisenstein, and therefore phi P is irreducible in Qx, and we are done. Okay, so that was about cyclotomic extensions. What do we immediately get? Do you see? Immediately we get the following. So for any prime P, zeta P is algebraic over Q. The minimal polynomial of zeta P over Q is just phi Px. And the degree of the extension Q round bracket zeta P over Q is P minus 1. Let's quickly look at why. We have nearly proved it. Let's complete the proof. So as we have seen, x raised to P minus 1 is x minus 1 times phi P of x. Now zeta P is definitely a root of x raised to P minus 1 because it's the Pth root of unity. But zeta P is not equal to 1, right? So it's not a root of x minus 1. So it's a root of phi P of x. So zeta P is a root of phi P of x. But phi P of x is monic and irreducible. So we know this by the theorem just proved before. Phi P is irreducible over Q, and it's also monic because phi Px is equal to 1 plus x plus up to x raised to P minus 1. Therefore, this has to be the minimal polynomial of zeta P over Q. And therefore, by definition, the degree of this extension is equal to the degree of zeta P over Q, which is equal to the degree of phi P, which is equal to P minus 1, because from this expansion itself, degree of phi P is P minus 1. And we are done. So now what immediately follows from this, where all the other roots are intact. So for any k between 1 and p minus 1, you can check this. GCD between k and p is 1. Therefore, each of these zeta p raised to k is a root of phi p of x because they are not equal to 1. Okay. So we'll immediately get that zeta p raised to k is algebraic over q. Minimal polynomial of zeta p raised to k is equal to phi p of x. And again, the extension q round bracket zeta p raised to k over q has degree p minus 1. Same argument. Okay. Because the minimal polynomials of all of these are the same. Okay. So just check this yourself. I have written this as a remark here. So these are cyclotomic extensions. More generally, for any n, since we are not going to prove this, but phi n of x is irreducible, it's an integer polynomial. So we get for any n, zeta n is algebraic over q. The minimal polynomial of zeta n is in fact phi n of x. And the degree of q round bracket zeta n over q is the degree of phi n, which is the Euler's quotient function phi of n, little phi of n. Okay. Now these field extensions, exactly these field extensions, q round bracket zeta n over q for any n, any positive integer n, these are called the cyclotomic extensions. When n is a prime p, we call it p cyclotomic extensions. But otherwise, in general, these are called cyclotomic extensions. Okay, so these were the special extensions that we just saw. All right, the extensions that you get by adjoining roots of unity. Okay, those are the cyclotomic extensions. And the polynomials, the minimal polynomials of these elements, these are the cyclotomic polynomials. Okay. So that's it about cyclotomic extensions. Now we'll go to finite fields in the next part of this lecture. So we'll stop it.